selective reading from one of the chapters of this amazing book that I've enjoyed reading into a lot. It's known as Interventional Fluoroscopy, Physics, Technology and Safety by Stephen Balter, who's a PhD. And this was recommended by my project manager to have a read into. And this book is Interventional Fluoroscopy, Physics, Technology, Safety. And it's an amazing book that I purchased for a very small price. And it was first published in, I think it says here, 1995, but the latest copyright is 2001 by Wiley, so they've taken it over. So I'll be going through chapter number 3, 4, 5 and 6. So let's see how much. So that's on page 31. Right, so I'll be talking about X-ray physics and the physics of image formation. So as image is formed by differential attenuation of the X-ray beam, the physical mechanisms contributing to differential attenuation are differences in thickness, density, and atomic composition, like elemental differentiation. And initially, uniform beam is modulated by structures possessing one or more of these differences. Details of the attenuation coefficients of materials are mentioned, and these coefficients have functional dependencies on the energy of photon and the atomic number of the material. So it's very obvious. I mean, the radiographic image of the chest is formed by all of these mechanisms. The portion of the beam passing through the liver experiences a great thickness of tissue, i.e. higher opacity, lesser transmittance than the portion passing through a soft tissue of the shoulder, which is fibrous muscular tissue. The lower physical density of a normal air-containing lung absorbs less radiation than the adjacent soft tissue of the mediastinum. The higher average atomic number of the calcium-containing ribs causes them to attenuate the beam to a degree proportionate to their thickness and density, i.e. elemental composition. The physical properties of an anatomic structure, I think that's a mistake, anatomic. It should have been the physical properties of an atomic structure. So the physical properties of an anatomic structure, such as the artery, the vascularity, musculature, denture, they can be temporarily controlled by injecting contrast media chemicals. For example, iodine is very active in masculine agents, so it basically what it does is it alters the atomic composition of the filling of the artery. CO2 is also used as a contrast medium. Surprisingly, didn't know about that. It functions by altering the physical density of the vessel lumen, the vessel diametric dimensions. Optimum visualization of these two fundamentally different kinds of contrast media are achieved by selecting different settings of the X-ray imaging system. So the subject contrast may be defined by comparing the intensity of an X-ray beam transmitted through a target relative to the transmission through its uniform surroundings. In mathematical terms, it's like this. So this is the X-ray beam modulation, for the differences in thickness, physical density, and atomic composition. It's T over B. And just to so the T is for thickness, and so the subject contrast is reduced by scattered radiation, the subject contrast is reduced by scattered radiation. The minimum usable net subject contrast for non-subtracted images is around 2%. The primary limitation on the minimum contrast is image noise. Radiographic grids are used to minimize the amount of scatter reaching the image receptor, the gantry. There's a cost to the resulting improvement in the subject contrast. The grid also absorbs some of the useful beam. This requires an increased irradiation of the patient and actually increases total scatter production as well. So the C is for contrast, and I is for intensity. Intensity before and intensity after, and the grid also absorbs some of the useful beam. So this is why a higher intensity of radiation, a higher quantity of dosage is required for the patient. Scatter production increases as the volume of irradiated tissue increases. So the more tissue there is in and around the area of interest, scattering of the light will increase in direct proportion. It's not a good thing, it's a nuisance, it's noise, and in addition to loss of image quality, the stray radiation around the angiographic table is always almost exclusively scatter. What we need to do is to collimate. Collimating the X-ray beam to a region of interest is a rare example of win-win situation. It's very difficult, like capacitance, it's in real life, this is very difficult. The efficiency is poor, and so the resulting reduction of scatter production improves the image and reduces staff exposure. But there are quite a lot of factors you need to control before you're able to effectively reduce the scatter and effectuate a high efficiency of diagnostic penetrance. So the diagnostic penetrative index improves at a high cost by controlling the scatter production. So the technology of X-ray production is discussed in Chapter 4. This section introduces the relationship between the electrical factors applied to the X-ray tube and the resulting radiation output and the line arc attached to it, linear accelerator. These factors are the voltage applied across the X-ray tube, the current flowing through the tube, and one of the other things is eddy currents, internal heating, and the circuit heating, in vacuo impedance reactance, and issues generated due to inefficient inductance. And in this chapter, histograms are used to display the detailed properties of the X-ray beam, and the histograms indicate the photon energy in kilo electron volts on the abscisca, and the number of photons carrying an energy on the ordinates. The rate of X-ray emission is proportional to the current flowing through the tube. The total quantity of emitted radiation is proportional to the current time product, which is charge. So current time times time is charge. So the quantity of emitted radiation is proportional to the charge. More radiation is emitted when the product of the current time is increased. So basically, in what you need to understand is for wave function, Huygens wave principle, intensity is proportional to the square of the amplitude cos theta. So I equals k a squared cos theta. Okay, but for particulate nature, it has to be ruled by de Broglie theorem, which is, so this is what you need to, it has to be ruled by these two. So intensity in general terms is power over area, and power is energy per unit time. So in this case, energy would be hc over lambda times time times 4 pi r squared, because from the machine, the point, it's coming out, and it's coming out as a cone, and it's spreading out. So we have to assume this to be either pi r squared or 4 pi r squared if you're taking a chunk out of it, assuming to be a sphere. In my opinion, we can't use the 4 pi r squared. We can only use the 4 pi r squared or 2 pi r squared, because it's a hemisphere at best. You could take it as a hemisphere, but you can't take it as a full sphere. So in my opinion, it would be this is how you'd calculate the intensity. Now, it said the intensity, the rate of X-ray emission was proportional. The rate of X-ray emission. So emission, the rate of X-ray emission was proportional to the current time product. Okay, so the current time. So the rate of emission. What is rate of emission? The rate of emission is photons per unit time. So photons per unit time. Photons is energy per unit time. Energy per unit time, which is power, which is, so basically intensity. So if because intensity is directly proportional to power, and power is being directly proportional to charge, Q equals IT dot product IT di dt. So sorry, small. So, and then so because of this, intensity has to be directly proportional to charge as well. If we put it in terms of what the book is saying, we would get out the following. So I equals P over T, IV over T, hang on, area, P over A, IV over A, Q, because Q equals IT delta. This is a small change, so we're using the small and lowercase for delta change, small change. So that'll be Q over T. So that'll be Q V over T A. So that'll be QV is work done, again TA. So so now we've proven that the book is telling us the truth, because I is always proportional to power and inversely proportional to area, and power is always proportional to current, and current is I equals Q over T. So power has to be proportional to charge, and when it's proportional to charge, it's proportional to intensity as well. So I proportional to power, proportional to Q. So that's how things are, because I equals Q over T, and I is proportional to charge as well. So that's why it's direct. It's serial direct proportionation. Now coming back to current and time, this increases the number of photons at each energy in the spectrum, this one, and more radiation passing through the target produces a brighter image. So intensity, brightness equals intensity. And amplitude equals intensity as well. So amplitude, brightness, as we may know from the electronic experiment, the single slit and the double slit experiment, brightness and amplitude, they are an expression of intensity. They are an expression. So now, increasing the kilovoltage, now this produces. However, the subject contrast between the two objects remains the same. Now, contrast is not the same as intensity. Contrast is a property of resolution. Resolution is independent of intensity, is linked to it, but is independent. Quality, indeed. So increasing the potential is more complex, because more photons are produced at each of the energies originally accessible. Photons are also produced at energies between the original and the new kilovolt. And the net effect on the fluoroscopic image is an increase in the brightness and a decrease in the contrast. So the intensity has increased, but increasing the voltage has reduced the resolution. So increasing the current increases X-ray production and leaves the subject contrast unchanged. But increasing the potential linearly increases X-ray production and reduces the contrast. So that is not feasible. This is not feasible for diagnostic approach. Increasing the voltage has a negative impact after a certain limit. It's counterproductive, whereas the current increase is useful because current is an expression of the energy, the electrical energy. So the graph is illustrating the spectrum of emitted X-rays as a function of tube voltage. There's no emission at low energies because of self-filtration by elements of the tube. Additional filtration is often... So we could see increasing the tube current proportionally increases the number of photons produced at each energy. So the current is feasible, but voltage is not feasible after a certain limit. And effective... So now this graph contains the Bremsstrahlung phenomena as well, and the karma. So I wouldn't want to go in there right now. Increasing the voltage increases the number of photons produced at each energy in the original spectrum and produces additional photons at higher energies, and they produce characteristic X-rays at a higher voltage as well. So the tube's output window is then modulated to enhance this effect. The maximum tube voltage determines maximum electron energy because we know, because of this formula, the kinetic energy of the photon is half times E times V, or half QV. So and the tungsten, because it's the tungsten filament, the tungsten is used for in the anode, and so the tungsten K characteristic spectrum is seen where it exceeds more than 69 kilovolts. So yeah, that's how things are. And then we talk about the interaction of X-rays and matter. This formula, this one, intensity naught equals exponent minus mu density times time. This is this formula actually compresses most of the previous material in the chapter into one line. For now, we'll all assume the absorber is a single element, carbon or an iodine, and that the beam is monochromatic. We have to assume that, although it's not the case. There are different ranges due to de Broglie manifestation. Mu is the mass attenuation constant coefficient, it's constant. E is the photon energy, Z is the atomic number, not the nucleon, but the atomic number, the bottom one. Mass number, Z, A minus Z, yes, so Z is the bottom number, and P is the physical density of the attenuator, not the element, but the attenuator, be it tungsten, osmium, molybdenum, and T is the path length through the attenuator, the path length through the attenuator, not the time, but the path length. Most of the radiation in a diagnostic X-ray beam is absorbed by superficial layers of material, and we'll show you a couple of plots that are absorbed by top 2 centimeters of carbon. So the attenuation coefficient of a material depends on X-ray photon energy and the atomic composition of the attenuator. Very typical, very predictable. And in this graph, we'll see the Bremsstrahlung. We'll see the X-ray spectra of emitted X-rays produced by tungsten target when energized from in a range of 50 to 110 kilovolts, and K characteristic radiations produced when energizing the voltage beyond 69.52 kilovolts. So this is the intent. This is a simple depiction of how things work. This is the induced intensity, the introduced intensity, and the energy, the Z, the atomic number of the attenuator, the density of the attenuator, and the path length of the attenuator, i.e. the thickness. That, I think the thickness should have been a better word. Thickness. And then we come down here and we see exponential attenuation of monochromatic radiation by carbon, top 2 centimeters of carbon at 20, 50, 80, and 150 kilo electron volts. Now, For iodine, so basically we can say, by using this graph, we can say mass attenuation coefficient for iodine and carbon as a function of photon energy. This is logarithmic graph, 0.1, 10, and 100. Logarithmic because of the large value of energies that can't be put on the graph paper on a linear scale. So and then on this side is the energy. So energy is on the x-axis, and the attenuation coefficient is on the y-axis. So it's attenuation coefficient, and then energy versus attenuation coefficient. So for iodine has a higher ability to function at a higher attenuation coefficient, so and carbon is at a lower attenuation coefficient. Please don't ignore Compton processes. Compton scattering is also part of it. The two of importance for diagnostic imaging are the photoelectric and Compton processes. There is photoelectric scattering, Compton scattering. There is the linear attenuation coefficient for carbon and iodine over the diagnostic imaging range. That's very useful in letting you know how things are working when you change the range of energies and how these. So carbon's pretty much constant, but in iodine there's a spike around about around about 25 kilovolts. There's a kilo electron volts. There's a spike, and then it declines from there onwards at a very steady gradient. The photoelectric occurs at a so the attenuation of the carbon is almost totally determined by Compton process, whereas the attenuation of iodine is summative of these two processes, photoelectric and Compton. So generally speaking, photoelectric scattering attenuation dominates at low energies, which is very intuitive. I can understand that. And Compton occurs at higher, because at higher energies there are more collisions, more bouncing, glancing, and head-on collisions, more energy, more stochastic, more vivacious stochastic behavior of the particles. And so you have to understand that the photoelectric process occurs when a photon interacts with an orbital electron. Going to the basics now, this process is most likely to occur if the incoming photon contains just a little bit more energy than the binding energy of the interacting electron. So this is the value for the K edge of iodine, and a photoelectric interaction with a particular electron level cannot occur if the incoming photon's energy is less than the binding energy of that level, i.e. KLMN or SPDFG, and the probability of the PE event decreases rapidly as photon energy increases. So the probability of PE event decreases rapidly as the photon energy increases. That's a bit. K orbital electrons of participate. Hang on. K orbital of electrons of participate in the photoelectric process for photons and energies above the binding energy. I think there's a mistake here. They should have of the element. I think they should have mentioned the element. They should have mentioned the element. So the process is more likely to occur if the incoming photon contains just a little bit more energy than the interacting electron. The probability of photoelectric emission event decreases rapidly as the photon energy increases. So what pulls the photon out is not the energy, it's the intensity, and the intensity is E equals hc over lambda over it's hc over lambda t to 2 pi r squared or pi r squared, and the products of PE interaction are a fluorescence photon and an ejected electron. The kinetic energy of the ejected electron is the difference between the energy of the incoming photon and the binding energy of the electron. The electron's energy is dissipated close to the point of primary interaction. The energy of the fluorescence photon is difference between the binding energy of the orbital electron and that of the low energy electron. So we can see that the photonic differential is very Schrodinger-like in its nature, whereas the the kinetic energy of the ejected electron is quite de Broglie in its functionality. And now we just talk about the fluorescent photons are emitted isotropically, like equal probability for any direction. So they are ejected, emitted equipotentially in all directions. The fluorescent photons may travel some distance before it interacts with another atom. So the level of interaction is very high. They're quite active in their interaction, and characteristic fluorescent photon energies may be used to determine the composition of a sample, so they're quite diagnostic as well. More uses than the ejected electron. The Compton effect describes, so this is basically, there's a formula for Compton scattering as well, which we will see soon. The Compton effect describes the interaction of an X-ray photon with an unbound electron at an angle. It should have mentioned at an angle. It's an angular interaction. The condition is fulfilled if the photon's energy is much greater than the electron's binding energy. The P of a Compton interaction declines slowly with increasing photon energy. The Compton effect is a main interaction process for diagnostic X-rays in soft tissue. It's of increasing importance for iodine. Energy is significantly above iodine's K edge. The products of a Compton interaction are scattered X-ray and a recoil electron. So that's why you have to have an understanding of the angular incidence, angular momenta in this case. Some of the incident photons' energy is carried away, dissipated, and away from the interaction by the recoil electron. It's locally dissipated. The scattered photon contains a portion of the energy in the incoming photon not transferred to the electron. For diagnostic purposes, the scattered photon carries most of the incident photon's energy. And in addition to this energy range, scattered photons are emitted isotropically, just mentioned here, due to Compton interactions with patients' tissues. Compound materials that are used are, it's polychromatic. It's basically polymerized, advanced polymerics, and an effort is made to find materials that have a linear single homogeneous attenuation coefficient, so that it doesn't induce multiple layers of scattering due to the inharmonious non-homogeneous material composition. So linear attenuation coefficients are obtained by multiplying the mass attenuation coefficient mu by the density, so mu times t, mu times rho. And the attenuation of the polychromatic beam is obtained by combining the monochromatic attenuation coefficients with the spectrum of the incident X-ray beam. Note the similarity of the mu of the muscle water and air over the entire energy range, which we did for iodine. This is why water is a good surrogate for muscle in phantoms. Phantom meaning empty statues used for research. Why measuring air dose tracks off, why measuring air dose tracks soft tissue dose. So, bit of a tongue twister. Why measuring air dose tracks soft tissue dose. See, these are the charms of reading. You have to, like this one, you have to, when you're reading, the author is telling many things that need to be, that you should write numerically as well, like EK equals work function plus MC squared. So that's how you need to, this is the work function, and this is the kinetic energy. So that's what's being said here. The attenuation coefficients of all materials decline with increasing photon energy. And the attenuation coefficients of all materials decline with increasing photon energy. So basically, attenuation decreases as the energy goes up. The attenuation coefficients of all the materials decline with increasing photon energy. For now, photoelectric absorption edges are neglected. Subject contrast decreases as attenuation coefficients decrease. This is true for differences in thickness and physical density. It's especially true for differences in atomic number. This is because mass attenuation coefficients of all the materials converge as photon energy increases. Now, you might remember we were talking about how a voltage ruins the resolution and current is good for it. So why can't we just, reduce the voltage and obtain the highest contrast and increase the resolution? The problem is the electrical energy consumed by an X-ray tube is proportional to voltage. So if you reduce the voltage, the energy production and the intensity would go down as well. Why? Because intensity is P over A and power is IV. So IV over A. So when the voltage goes down, the power goes down, so the intensity goes down, and the energy goes down as well, because hang on, because this is how it is. So this is why when you put the voltage down, the energy goes down, the power goes down, and the intensity goes down. Efficiency of the X-ray production is proportional to kilovolts squared efficiency. Now this is the efficiency, not the intensity, not the energy, not any other. It is efficiency. Efficiency is output over input times 100. So that's why. Because of the variation of absorption coefficient with the energy, the intensity of the radiation transmitted to a patient is proportional to voltage quadrupled or pentupled. Imaging at high voltage minimizes the electrical load on the system and the radiation load on the patient. So that's why you can't reduce the voltage. Controlling the voltage is a key element in most feedback circuits, i.e. with the reverse bias, forward bias, and the electronic microchip controlled circuits. However, the contrast between iodine and tissue decreases as voltage increases. So that's also a problem. So if you increase the voltage, iodine would stop functioning as a compound. As a contrasting compound. The visibility of the vessels will therefore decrease with the increasing voltage. So iodine visibility decreases in thick patients, thick as in with thicker skin density, thicker bone density, because a higher kilovolt is needed to push through enough of the beam through the patient. This larger irradiated volume generates more scatter. So unfortunately, it has its negative aspects as well. Beam filtration, the spectrum of photons produced by an X-ray tube, includes energies ranging from a defined maximum determined by peak voltage applied to the tube to a less well-defined minimum. The X-ray tube's anode and window absorb low energy soft radiation and high energy hard radiation, because hard and soft radiation is basically low energy, low intensity, low power. Because soft radiation is also easily absorbed by tissue, it contributes to patient's skin dose without contributing to the image formation. Aluminium has an applicable photoelectric absorption coefficient at low energies, as in other materials. I mean, although aluminium is toxic, but here it's slightly useful. We don't know about the long-term chronic impact of using aluminium for the patients in radio diagnostic procedures. As in other materials, the attenuation coefficient of the aluminium decreases with energy. Placing an aluminium filter on the output port of an X-ray tube reduces fluoroscopic patient dose by preferentially absorbing low-energy photons. This process is called hardening the beam, i.e. collimating the beam or taking the scatter off of it. This is seen in figure 3.9. The quality of an X-ray beam can be defined by its half-value layer. Half-value layer of a beam is the amount of material needed to reduce the beam's intensity by a factor of 2. The physical properties of the absorber and the spectrum of the incident X-ray beam determine the half-value layer. And we're assuming that all of it is monochromatic, which it isn't in a real X-ray tube. It's not. It's polychromatic, and it's coming out from an X-ray beam anode, X-ray anode. It needs to be hardened, it needs to be collimated, it needs to have its half value layers sorted out. So half value HVL of a typical polychromatic fluoroscopic beam is around 3 mm of aluminium or 4 mm of 4 centimeters of tissue. So you can see that only 3 mm of aluminium can harden the radiation emission, whereas you'd need 4 centimeters of tissue to do that. So that's quite a lot of extraneous, extra unwanted exposure on the bone and skin of the patient, which aluminium can take off. HVL increases with increasing filtration and the X-ray tube voltage, and the required minimum for it for a diagnostic system increases with voltage as well. So obviously more voltage, more scattering, and you need more aluminium to absorb it. So these requisite values are tabulated in the FDA regulation. Here it would be European Medical Physics Society Association that would regulate this, and compliance with these regulations ensures that the non-penetrating radiations falling off the patient's skin is held to an acceptable minimum, and the verification procedures are mandatory. Increasing the beam hardness increases penetrative index of the beam through the patient, and this means that less radiation needs to be entered into the patient to produce a constant. This means that less radiation needs to be entered into the patient for producing a constant exit dose. Thus, harder beams reduce patient entrance dose. So harder beams do the work in lesser amount of exposure. Most interventional systems substantially exceed minimum values of HVL. Filtration between an X-ray tube and the patient also absorbs some of the image-forming photon energies. Under most circumstances, adding excessive filtration further reduces the skin dose at a cost of a disproportionate increase in X-ray tube loading and an undesirable decrease in the subject contrast. The resulting harder spectrum has more of its energy away from the iodine K edge. This reduces iodine contrast. In addition, the effective output of the tube is reduced. When this happens, the imaging systems often increases its voltage. This further reduces contrast. There are two exceptions to this rule. A thin 50 micrometer copper filter is important for interventional neuroradiology. Some newer systems use combinations of higher power X-ray tubes, copper filters, and copper anodes, and special collimators, collimating anodes that I know of, and special system regulation curves to better optimize the balance between patient dose and iodine contrast. Now, the summary for this chapter. X-ray outputs controlled by voltage, current, and exposure time. X-ray attenuation depends upon thickness, density, atomic number, Z, as well as the X-ray beam spectra. Depends on intensity, power, energy, and the formula I wrote earlier was so that's how it is. So that's the end of this chapter number 3 that started from page 31, and we've done about 10 pages of it, and it's been a very cathartic experience to learn about the impact of voltage and current, and how it interacts with contrast and the role of aluminium, and how mu, density, thickness, and Z are linked to it in this whole process. So thank you very much for paying attention and staying with me throughout the video, and I hope you progress in your understanding of radiodiagnostic operational schemes. Thank you very much. Have a lovely day. Take care. Bye now. If you've got any questions, I'll be more than happy to post answers down below in the comment section. Take care. Bye now.